I'm talking about some new results on the QAOA, the quantum approximate optimization algorithm. And I'm actually going to talk about something that came out on a paper yesterday. So it's very topical, I hope. This is work I've done with my collaborators who are listed there, Fernando, Michael, Sam, and Hartmut. And these are new results on the QAOA, which I think are going to help us run it in practice. But in order to go over this, I have to do a little intro to the QAOA, which is the quantum approximate optimization algorithm, which was developed by me and my collaborators, Jeffrey Goldstone and Sam Gottman. So for those of you who know what the QAOA is, this is going to be a little review. And then I'm going to go to the new results, okay? And there's this clock thing that's adding time. Now it's going backwards. Okay, that's good. It was going the other way before. All right, so let's go over what this is. I'm interested in combinatorial optimization. And these are problems where you have n bits and you have clauses. And clauses are constraints on the subsets of the bits that say whether a certain bit assignment is satisfied or not. So for example, in 3-SAT, you have clauses which look at 3 bits and are happy on 7 out of the 8 assignments of the 3 bits and unhappy on 1 of the assignments. And there are many examples of combinatorial optimization problems. And the goal in combinatorial optimization is typically to find a string that satisfies as many of the clauses as possible. If you can find the string that satisfies all the clauses efficiently, then you would have an algorithm which would solve all the problems that computer scientists care about. It's believed such an efficient algorithm does not exist. The statement that an efficient algorithm for maximizing that function, which is the sum over the individual clauses, maybe I didn't say that. I have a cost function which sums over the individual clauses, the individual clause cost functions. And so if you maximize that, you find the assignment that satisfies as many clauses as possible. Now, you know, sometimes the best is the enemy of the good, and so searching for the best solution may be too much. And very often we're interested in something called approximate solution, where you output a string, z, you evaluate the cost function, and you want the ratio of what the cost function value you outputted divided by the best possible to be big. That's the approximation ratio. And this algorithm is designed to look for solutions that have a good value of the approximation ratio. So the ingredients of the QAOA involve unitary transformations which act on a quantum computer. The first unitary transformation we define involves the cost function itself and a parameter gamma. And so it's of the form e to the minus I gamma c. That's a unitary transformation, which is a product of commuting few-bit operations. The other operator we care about, b, is the sum of the sigma x's. It's just a transverse field in the x direction, if you think of it in spin language. And we have a unitary transformation, e to the minus I beta b, which is the product of, written as the sum, becomes the product of individual spin rotations around the x direction by an angle beta. And we start in the state which I call S, which is the uniform superposition over all possible input strings. And this happens to be a very easy state to construct. So now the algorithm works in the following way. I'm not going to go into many details. But what you need to do to run the algorithm is you need to specify 2 p angles. We have a parameter p which describes the depth of the algorithm. So there are going to be p angles gamma and p angles beta. And then the way we construct this state, this is the quantum state we construct, gamma beta. And what it is you take the initial state and you hit it with the exponential of the cost function with angle gamma 1. Then you do the rotation about the x direction by beta 1. Then you hit it with the cost function. Then the rotation, the cost function. You alternate these and you build that state. And this is an easy state to construct on a quantum computer. If p is small, and I'm going to be very interested in p small, the circuit depth is at most mp plus p. So what we want to do, though, is we want to evaluate in this quantum state the expectation of the cost function. So, and the goal is to choose the parameters so that you drive the cost function up. We want to figure, and we're going to talk about how you might do that, but that's the goal. We want to build the quantum state so that the expected value of the cost function is high, and if you do that, that means that if you make a measurement of the state and you get a string, you'll find a string with a high value of the cost function, and that's our goal. So, how might you do that? Well, people talk a lot about these variational approaches. And the idea there is you start with a fixed p, you fix it, and you start with some angles, and you use your quantum computer to make the state. And then what you do is you go and you measure a string, and you get a string z, and then you evaluate the cost function on that string with a classical computer. So this is a lot less involved than what you do when you evaluate the expectation of the energy in a chemistry experiment or a physics experiment, because here all you do is measure a string and then evaluate the cost function. Now, you might repeat that with the same angles, and if you repeat it a few times, then you get a good estimate of the expected value of the cost function, the quantum expected value. And then what you might do is have an outer loop, which you try to run, which helps you change the angles in an attempt to go uphill. And that's the outer loop part. People talk about these hybrid algorithms where you make calls to the quantum computer and then you do something classically to change the angles to try to make it better. Make a call, make it better. And so this is the general variational approach which is used in many contexts. But now let me talk about an example. That graph looks like a fish. I didn't mean that. I just drew a graph. That's just supposed to be an arbitrary graph. I'm going to just draw a graph with n vertices and m edges. I didn't mean to make it planar. I didn't mean to make it look like a fish. It's just a graph. And what we're going to do is we're going to assign plus or minus 1 to each vertex. And in the max cut problem, there's a clause for every edge. And the clause is satisfied if the bits disagree, and it's not satisfied if the bits agree. So the idea is to put plus 1s and minus 1s on the vertices of the graph in such a way that you maximize the number of disagreements. This is called max cut because you can view it as a division of the graph into two sets with a cut between them. But I call it disagree. The idea is to maximize the number of disagreements. And typically, you can't do, if you have a triangle, you can't put down assignments so that every edge is satisfied. That's called frustration. And so sometimes you can think of this as a frustrated system because you can't satisfy all the bonds. And so the challenge becomes maximize the number of, find the string which maximizes the number of edges on which the bits disagree. It's called max cut. So it turns out that at p equals 1, we were able to prove that the quantum approximate optimization algorithm will produce a cut that is at least 0.6924 times the optimal cut. And the reason that this was really pretty interesting is we were able to do this for all instances of max cut on 3 regular graphs. We restricted to 3 regular graphs. 3 regular means that every vertex has 3 friends. There are 3 edges coming out of each vertex. And the reasoning, again, of course, we did this by analysis by hand, but we proved that if you had a quantum computer with 1 trillion qubits, it would get a cut this good. Now, this does not beat the best classical algorithm. I'm not saying it does. But it was still, it was one of the only times in optimization that we had an actual worst case performance guarantee. And that was significant to us. But so to say that the 0.6924 improves on random guessing, if you just guess a random string, if you just throw down a random string, you're going to satisfy half the edges because you just have a 50% chance of satisfying. So it's very easy to get an approximation ratio of 0.5. Now, I want to say one other thing. I want to look at that problem we call it the ring of disagrees, where it's a very simple problem. I want to find the max cut. Now, we all know we can solve this problem with our eye, and you just go up, down, 1, minus 1, 1, minus 1, 1, minus 1, and you circle around. If they're an even number of edges, you can do it perfectly. So this is not a hard problem. But the QAOA gives an approximation ratio of 2p plus 1 over 2p plus 2. So the approximation ratio gets better and better as you increase p. It's independent of n. But I just want to say one thing about it. If you look at p equals 1, the approximation ratio is 3/4. But what this algorithm will do is it will produce strings which satisfy 3/4 of the edges. But if you look for the probability of finding the best string, it will be exponentially small. So the quantum approximate optimization algorithm is producing states which have that approximation ratio. It's not just finding the best solution with a certain fixed probability. And in that sense, it's very different than the way a lot of people envision it as just seeing how well it looks for finding the best solution and saying what fraction of the time does it do it. That's not what it's doing. Okay. And I'm just going to tell a little story because it's sort of amusing about a different problem called MAXI 3-Lin 2, which is the next problem we looked at. This is a problem where you have equations. I'll go through it sort of fast. You have equations, and so you have n variables and m equations. And the way it works is to specify an instance of the problem, I tell you a set of triples. I say variable 1, 19, and 22 are in the first equation. And the first equation says that they should add up mod 2 to either be 1 or 0. So I also have to specify whether it's a 0 or a 1, what I want them to add to. Now, typically, if you have a lot of equations, this thing cannot be satisfied. In other words, you can't find strings which satisfy all the equations. So the task is to find a string that maximizes the number of satisfied equations. And this is different than max cut. It happens that, again, if you could find the string that satisfied the absolute maximum number of equations that could be satisfied, you would be solving an NP-complete problem or NP-hard problem, and then you would have the biggest result in computer science of the century so far. So what we're going to be looking for is not finding the best solution, but finding a good solution. Let's talk about that. So again, for this problem, if you guess a random string, you're just going to satisfy half the equations because you can just look at it and see that the equations add up to 0 or 1. And so if you have 3 variables, they have 8 possible assignments, 0, 0, 0, 0, 0, 1, etc. And so half of them will add to 0 and half will add to 1. So if you guess a random string, you'll satisfy half the equation. And that gives an approximation ratio of 1/2. But it turns out, which is kind of remarkable, that if you had an algorithm that got 1/2 plus epsilon for any epsilon, in other words, if you had an algorithm that provably improved on the half, instead of having 0.5, you got 0.50001, but you could prove it worked in all cases, then P would equal NP. That's astonishing that they could show that just improvement on random guessing is so significant. This follows from very deep work in computer science over the last 20 years. Anyway, so now what we're going to do is we're going to make it a little bit easier, the problem. The way I'm going to make it a little bit easier is I'm going to tell you that every variable is in no more than D equations. So now I've given you something. I've told you something. I've said, I haven't told you we're considering, these are worst case results. So I'm telling you, giving you a little hint. No variables in more than D equations. It turns out that in 2000, there was an algorithm for that gave you a half plus constant over D. If you're confused why constant over D is not as bad as epsilon, we can talk about that later. But it isn't, trust me. So anyway, that algorithm existed in the year 2000. It was due to Hofstad. And then what happened in 2014 is we got a quantum algorithm that got a half plus constant over D to the 3/4, which was an improvement. For at that moment, we had a quantum algorithm that was exponentially faster than the best classical algorithm for this problem. So Scott was excited about it, and he blogged about it. And as a result of his saying this algorithm was so great, this group of computer scientists got together and improved on our result. But I just want to show you the list of computer scientists. It's like, this is a list of the top computer scientists in the world from every country. This is like, you know, United Nations Special Forces team, SEAL team going after 3 guys. It wasn't nice.
But you didn't need all of them to do it. That's like they each did it independently.
Okay, fair enough. They each did it independently, got together. But they still get, so that's even worse, because they ganged up on us. They got together and went after us. It wasn't nice. Anyway, I lived with it. You know, it's 11. I said 10. I can't even count. There are 11 of them. Anyway, fine. So anyway, it turns out that we then went back and looked at our thing, and we actually could get 101 d to the 1/2 log d. And on typical cases, random cases, we actually get 1/2 plus 1 over 2 square root of 3e Napier, you know, Euler's constant d to the 1/2. Anyway, I don't want to talk about this anymore, but it was a kind of a great little adventure in quantum computing where we stimulated the classical people to do a little better. And, you know, I still think this is an open area. So now I want to talk about the new stuff. So let's go back to MaxCut. But now I want to talk about instances that come from a fixed distribution. So now I'm imagining that I'm going to do MaxCut, but I'm only going to I tell you, all my instances come from a distribution. For example, they all may be 3 regular graphs, or each edge may be included with probably the 3 over n minus 1. The reason I take that is if the probability of including an edge is 3 over n minus 1, then typically your graphs have valence 3, have degree 3. Or some other distribution. And so here I'm not talking about worst case, but I'm just talking about typical case. And what we found is that we can demonstrate that if we fix the parameters, gamma and beta, then for typical instances, the value of the cost function is the same for all instances. Well, after you think about it for a while, it's not so surprising, but it was quite surprising to me. So what it means is that you toss an instance, you fix the parameters, you evaluate that, and then you do it again with another instance, and you'll get the same thing. And we can show why that is, but in advance of that, let me show you the data, the kind of data we get, just to give you an example of how concentrated it is. So here I'm going to look at 20 vertex 3 regular graphs. So I toss them, 20 vertex 3 regular graphs, and I look at 25 samples. And let's look, and now for P2, 3, 4, 5, 6, 7, I fix the angles in the first column. So okay, let me go over something. If I have a 3 regular graph with 20 vertices, it has 30 edges. So that means the cost function, in principle, could go from 0 to 30, from satisfying none of the clauses to all. These graphs, you can't satisfy 30 because they're always frustrated. They satisfy typically 26, okay? So what I do is I fix P, let's say P is 2, and we find some angles on one graph which has a low value for the cost function. The typical value of the cost function, since there are 30 edges, is 15. You kind of typically satisfy half. So we pick it to be the first set of angles to give us a value of 6. But look at the standard deviation over the 25. I mean, all 25 graphs have roughly the same value. Then we go to a random choice of the angles. Well, with random angles, you expect the expected value of the cost function to be about 15, because that's right in the middle. And again, the standard deviation is small. And then we go to high values, where I choose the angles to push it up. Now, we do this for P of 2, 3, 4, 5, but every time, the higher P, the easier it is to push it up to high values, because you have more parameters to play with. And it's also the easier it is to push it to low values, because I have more parameters. So we're not optimizing the parameters, but we're just picking the parameters to get rid of the random toss in the middle. Because I don't want you to say, well, all your results are based on the fact you have a random graph with random angles. So I push away from that into the wings. And wherever we push, we see very good concentration. I mean, if you go to the high end, for example, at P equals 7, these graphs have max cut values of 26. So without a lot of work, I can find angles on a graph that it satisfies 25 of the constraints out of 26, but then all of its friends with the same angles also have that value. So this gives a strategy for random instances of these kind of problems. Pick an instance and work very hard to get good angles. Put all your work into getting the good angles on that one instance, because we've told you that the whole landscape is instance independent. So you pick an instance, you work very hard to get good angles, and maybe this requires many calls to the quantum computer. But once you have those angles, you can use them for the other instances, and then you may wish to refine it on the other instances by going up a little bit more. So I think this is a nice strategy. I would like to tell about another finding, which I think is in a way even more remarkable, which if you toss let's say I do the following thing. I toss a random graph at 10 bits. And I go to P equals 8, and I find very good angles with the computer, with my laptop. And I get an approximation ratio of 0.98 for this one graph. Now, I take those angles, and I go to 24 bits. Okay? And it's same angles, and I toss a random graph. And suddenly, I did this, I think, 25 times or something. The average approximation ratio is 0.934. So that's kind of interesting, because it says you can pick the angles at low, on a random graph at 10 bits. I fix 16 angles, because P is 8. And then I use those 16 angles at 24, and it still works. And there's no further optimization done here. So I just use those angles at 24. I could refine it, but I didn't. So, so there's a leapfrog strategy. So suppose you want to use a quantum computer at 100 bits to find good cut on a random 100 vertex graph. You have a quantum computer. So what I would suggest doing is toss a 20 vertex graph from the same distribution. Run the classical computer at P equals 6, let's say, to get 12 good angles. Because you can do this on a classical computer. Now you go to your quantum computer, which is, and you say, I'm going to use half the vertices. I use 50 of them. And I toss a random 50 vertex graph from the same distribution. And I run the quantum computer with these angles, and I know I'm going to get a good value, but then I refine it a little bit to make them a little better. And then I take those angles, and I go to the 100 vertex graph, and I think that this strategy will give you a good cut. Now, what's the point, in a way, is that we found new strategies for running the QAOA that greatly reduce the use of the outer loop to hunt for good parameters. Because I'm giving you two pathways to do that. One is to toss a random graph and work very hard on it at the bit number you want to work with. The other thing is try to look for your angles at much smaller instances, and they'll probably also work. So I think this is significant because, you know, people are really interested in finding out ways to run algorithms in practice. And if you can reduce the number of calls to a noisy quantum computer, I think it's just manifestly advantageous. So, you know, that's what we've done. And that's basically the end of my talk. Okay, thank you. So I'm open for questions.
I've got 11.
Yeah. Who? Is there somebody who wanted to ask something? Oh, Eleanor. Great.
Do you have a sense for the hardest problems within a class for classical algorithms, whether you also see this stability of the parameters, or
well, I don't know. No, you have to. I can't say that unless you tell me what the classical algorithm is.
Right.
I mean, for what a classical algorithm?
Yeah, if you choose one.
Like, well, I don't know. I mean, I don't know. I don't do that. I mean, you have to tell me what the classical algorithm is. What, you know, how does the one thing that's very important here. We have some. Oh, I should also say we understand this. I didn't say that. I only showed you my numerical evidence, but we can prove this occurs for fixed p and n large. I can prove this happens, so we have a math proof. And the other thing I didn't say is that if p is big and n is, if p is big, like in those, you see in those numerical examples I did, I had p of 8 at 20 bits. That's huge. That's a very high value of p. And I can also explain why it happens. I have a sort of very good mathematical story, which is not a proof, but it's right. You know, so that's what I care about. You know,
yeah, one follow-up.
You know, truth before proof. So anyway, it's true. So and anyway, I didn't say that, but then you'd have to, I did say that, excuse me, but then you have to look at the proof technique. And the proof techniques always require the fact that the cost function is a sum of individual terms. So it would matter to me whether your classical algorithm knew that or not. See, it depends on the nature of the classical algorithm. But, you know, basically our arguments, they use things like the law of large numbers, which you could apply to many situations. So I can't say about classical algorithms. I have not discussed, if anyone didn't notice, I did not discuss performance relative to classical algorithms. I just talked about how we could reduce the number of function calls to the quantum computer. Okay?
Fair enough. In looking at your proof, very, very briefly.
Yeah, because the paper came out yesterday, so thank you for looking at it.
It relies on graph properties for max cut. That certainly generalizes to some extent. Do you have a sense as to where the boundary is for where that would, which graph problems that will apply to and where not?
I think that, you know, I think we kind of say it. I mean, well, I mean, we use the term reasonable distributions, which is kind of slippery. But, you know, I think this is true for all reasonable distributions. But I think oh, yeah, well, I don't know. Probably it works for, you know, I would bet that this will work on max 3-sat if you fix the ratio of the number of clauses to the number of bits to be fixed. I don't see, it's the same thing. Yeah, I would think it would work on max 3-sat or max 2-sat. Yeah, I would guess that it's the same. And also, you know, it was observed actually by Gossett and Bravi that they did, you see, Gossett and Bravi last summer wrote a very beautiful but dense paper about how to do classical simulation of quantum computers. And they applied their methodology to the quantum approximate optimization algorithm. And they looked at max E3 Lin 2. And they said in their paper they noticed that the function value was independent of the instance. So, you know, we referenced them. But that was, it was noticed on max E3 Lin 2 by Bravi and Gossett. Yeah, so that's an example of a different problem. That doesn't look at all like max cut.
Hi, Eddie.
Yeah, you know, it's funny because all I hear is a voice. Oh, thank you. That's a little flawed in this system.
So you said the word, so let me ask you the question. What's a reasonable distribution? What do you mean by reasonable?
Reasonable?
Yeah.
I don't know. Reasonable means that, like, you know, can I give you by example? I think a reasonable distribution is like fixed degree graphs for max cut, where you're uniform over all the graphs. I think a reasonable distribution is a Rennie graph where you have the probability of including an edge is a fixed over n. And then the average, if it's k over n, then the typical valence will be k. And that, you know, our methods will work for that. I think apparently I bet it'll work for random instances of max E3 ln 2. I mean, I don't know exactly what reasonable it means. It's not weirdly pathological.
Just define it to be anything for which your method works.
Fair enough, yeah. Yeah, I mean, you just can't say that in a paper. So, you know, but believe me, we discussed this. And there were members of the collaboration who were questioning the use of the term reasonable. But then, of course, the most senior members, the older members of the collaboration are comfortable. The younger members are not. And that's, and that's basically the way it goes, you know. It's like the younger they were, the less they liked it. The older they were, the more they liked it. Makes sense. Okay, anything else? Okay? All done? Sure.